Good day. Today we are going to discuss Module 8 of CE 2121 Topographic Surveys. So we define now topography as the study of the shape and features of land surfaces. The topography of an area could refer to the surface shapes and features themselves or a description of it. The techniques used for topography would be direct surveys, remote sensing, and aerial photography. There are different forms of topographic data. This includes your raw survey data, remote sensing data, topographic mapping, digital elevation modeling, topological modeling, and for our topic, we'll be focusing on topographic mapping. So we have your topographic surveys, which is typically published as a map series made up of 2 or more map sheets that are combined to form a topographic map. A topographic map is defined as a type of map that is characterized by large-scale detail and quantitative representation. So this representation now would include the height or the elevation, the depth, size, and location of reliefs, usually using contour lines to show both natural and man-made features of a given parcel of land. When we say contour lines, these are now lines connecting places of equal elevations above or below sea level. When contour lines lie close together, they represent a steep slope, and lines that are far apart would represent a gradual slope. The purpose or objectives of a topographic survey would include to collect survey data about natural and man-made features of land, as well as its elevation. Also, to determine relative location of points or places on Earth's surface by measuring its horizontal distances, difference in elevation, and directions. The uses of topographic surveys would include any type of geographic planning or large-scale architectural and civil engineering works. This is used in applied sciences and many other geographic disciplines. Topographic surveys are also used and applied in mining and other earth-based disciplines. So producing topographic maps and profiles and establishing vertical and horizontal control for accurate definition of locations. So we have reliefs, ridges, and valleys. When we talk about reliefs, this is defined in geography as the difference in elevation of the highest and lowest elevation points in an area. So ridges would now be a type of relief which defines the highest elevation points such as mountains and hills, while valleys would represent reliefs of lowest elevation points such as plains and the like. So we have here a relief is defined as a lowest, so this is a valley, and we have here the highest points or your ridges. So the difference between your highest and your lowest point is your relief. So we have here a shaded relief map and a raised relief map. So when we talk about shaded, means it has colors on it. And when we talk about the raised relief map, it is usually of three-dimensional representation of topography. So we have now the methods in representing reliefs. So we have the spot heights, which are also called the spot elevations. So this is defined as the elevation of a point on a map or a chart. They are usually indicated by a dot accompanied by a number indicating the elevation. It is used principally to indicate points of important features such as summits, SUGs, highways, and the like. So for this given contour map or topographic map, so we have here this dot with a number 534. So it is a spot height which defines now the Nakologe summit, which is at an elevation of 534. So other spot heights in this contour would include this point. So we have 480. So it represents the elevation of Balinafhun Shoge. Okay. So next method, we have your hachures, one of a series of short parallel lines or hatches drawn on a map to indicate topographic relief. So it indicates the slope and the degree and direction of the slope or of the relief. So it's drawn in the direction of the steepest gradient. So a short and thick stroke represents a short and steep slope, while a long and thin stroke represents long and gentle slopes. So we have here an example of a topographic map made up of hachures. So this one is a contour line with hachures. The tick marks now, or the hatches on the contour line, represents the slope and the direction of the slope of the area. So this area, since the shores are pointing towards the center, so it means it is a depression, or the elevation is moving or is decreasing. Next method, we have layer tinting. So it involves coloring areas between selected contours in different colors. Darker shades would mean higher elevations above sea level, and the altitudes are represented by each tint indicated on the maps and charts as legends. Colors are sometimes referred to as elevation tint or layer tint. So these are examples of reliefs with the use of layer tinting. So you can use several colors to indicate the elevations of the topography, or you can use a single color with different shades. So for this example, the brighter color red represents higher elevation, and for this example, the darker color or shade of red is the highest or higher elevation. No color would indicate zero elevation or lower elevations. So next method, we have shading. So for shadings, this now involves the use of shadows to emphasize topography of terrain. And an example is your hill shading. So this shows the shape of hills and mountains using shades of gray, and is used to indicate relative slopes, mountain ridges, but not the absolute height of hills and mountains. So these are examples of shading or reliefs represented by shading. So it's like there is a bright light here and a shadow is casted on the other side. So the darker the shade means there is a higher elevation. So for this part, for example, this is of low elevation, the lighter shades. Okay, so next we have relief or terrain models. So these are sometimes called topography model or composite model. It's a combined digital elevation model or DEM data over land with digital bathymetry model or BDM data over water-covered areas to describe the Earth's relief. So this is a three-dimensional representation of your Earth's surface. So you have different layers. So we have here your single sheet or a blank space, which represents here a building. We have here your road. This is the map for the water lines or water source. This is your contour map. So you layer it out, combine every data from this maps, and you'll be arriving at a relief or terrain model, a 3D representation of the reliefs. So you have different types of terrain models. So based from the contour lines on sites, gather data on the site, you can form a 3D model with a mesh, or this is a grid pattern, or you have here a triangulated terrain model or a step type model, and we have here a combination of a triangulated contour. So this type of representation of reliefs are more of software based. So we have ridge and streamlining. So this is used to emphasize location of low and high ground. This is used in aerial photographs. So stream and their tributaries would be represented by blue solid lines, and the main ridges or the higher ground would be represented by brown dashed lines. So for this given contour, we have here our stream or our river, and then this brown line, reddish or brownish line, represents the ridge of your mountains. So we have here another example. So all the blue lines here represents the tributaries of this lake, and then we have here your dash line, which represents the ridge of the mountain. Next method, we have the Subaquase Contour, which is a topographic map that often includes areas of navigable waters, such as seashores and large inland lakes. So they portray the relief of ground underwater. So these are examples of subaqueous contours. So this one is a subaqueous contour of Antarctica. So you can see the depth of water based from this topographic map. So this is another example. So you can see the depression of the lake Huron in this map. So next method of representation for relief is your form lines, which are drawn when there is not enough vertical control point available, or when the surface is too irregular or intricate to contour. So these are example of your form lines. So if we have not enough control points to put on our elevations, we will add some form lines to indicate the shape or contour of our topography. So form lines usually would not indicate your elevations. And last method for representing reliefs would be our contour lines, which will be our focus in this subject. So contour lines, as we have said, are curved lines that connect points of equal or same elevations. They are the most distinguishing features of a topo map or a topographic map. So this is an example of a contour line that represents the topography of different land formations. So this one represents now the highest point of this hill. This one would represent this. So this is a representation of this mountain. So this is a representation of this plateau. So this is a one-sided mountain. So this is another plateau. So these are two hills. So it's the representation of these two hills. So for contour lines, so in our two-dimensional map, so you will see these lines, and this represents the difference in elevation of your formations. So there are three kinds of contour lines. We have the index lines, which are the thickest contour lines, and they're usually labeled with the elevation at one point along the line. The second kind of contour line is your intermediate lines, which are thinner and more common lines between the index lines. And typically, one index line occurs for every 5 intermediate lines. Supplementary lines would be appearing as dotted lines and would indicate a flatter terrain. So examples of your index line. So it's a boulder line with the elevation on it. And then we have your approximate, intermediate, and your supplementary. So for approximate lines, these are now contour or a special type of contour line, which is somewhat like your form line, as it would follow the contour of the index and the intermediate lines. So this would represent now, if we want to have a finer contour map, we have your approximate contour line. So it's represented by dashed or dotted, longer dotted lines. So we have your contour intervals. This is a constant vertical distance between two adjacent contour lines. And the selection of contour interval would depend now on the relative cost of topographic survey. So this would include the time and the expense of the field, how wide your survey area is. So on the purpose of the map. So is the map going to be utilized for detailed design? The nature of the terrain. So is required to produce a suitable density of contours. So if we have a flat terrain, then we could use a more farther or longer contour intervals. But if we have a steeper topography or terrain, then we'll need a more control points. Then we have the scale of map. This one now, or the contour interval now, will be the inverse ratio of the scale of your map. So we have the formation of your contour lines. So this contour lines now will form, or the formation of your contour lines will represent different types of land formations. So we have your peak ring, which is the innermost ring at the center of several contour loops, almost always represents a peak or the highest elevation. So sometimes the peak will be represented with the small x and a number, which denotes the elevation. And then we have your deformation ring, which is the inner ring that indicates a depression or the lowest elevation, which the map will show with the series of small tick marks pointing towards the center. So next we have the cliff, which is represented by two or more converging lines that appears as a single line. Though some cliffs may not appear on the map, for example, if the contour interval is 50 feet, a cliff of 40 feet might not appear on your maps as it is smaller in elevation compared to your contour intervals. Next, we have your valleys, or also known as draws. So these are formed by a sharp V or a U-shaped contours. Streams and rivers would be represented by blue lines, and this will run through the center of the V-shape or your U-shaped contours. So valleys or draws will follow the rule of V's, wherein the V-shape will always point in the opposite direction that the water is flowing. So it points toward the higher elevation. Next, we have your ridge line, which is an elongated peak not forming a fine point. So instead of a closed inner circle, a ridge line can look like a big oval. Next, we have your saddle, which is a low-lying area between two higher points of elevation. So this shows the quickest route through hilly areas and appears as an hourglass shape between two concentric circles. Next formation, we have your ledge, which is a flat area on the side of a mountain. It appears as a protruding U shape that points away from the. So we have your examples of the contour lines formation or terrain features. So we have here your hills, we have here your spurs. So lines that are near each other would represent steep slopes. Then we have here your gorge. So we have your cliff. So for some maps, they would appear as one line. We have here your valleys where your river would pass through at the centers. So we have here a different diagram for your terrain features. So hills would be more or less circular in shape, concentric circles. So a saddle would represent an hourglass-like shape. So this one represents this portion of the formation between two hills or two mountains. You have here your ridge. So this is the center of your mountain or your hilltop. So we have your valley. So this is the water source. This is your tributary. So next we have your cliff. So for some maps, they would appear as one line, but they are actually like stuck together. So we have your depressions. So we have hachures or hatches directed towards the center, indicating a decrease in elevation. Then we have your spurs. So this is the feature between two mountains or hillsides. You have your dross, which are examples of your valleys. Okay, so next we have your contour map construction. So there are different methods of locating your contour lines. So this would include estimation, which is suitable for small scale maps where ground form is not too irregular. We also have your rubber band method. So we use a rubber band which is stretched between plotted points so the points fall at scale divisions corresponding to their elevations. We also have the analytical method or our interpolation. So we assume that the slope between two adjacent points established is uniform. So we also have your triangle and scale method. So it's an application of geometric method of dividing lines into convenient number of equal parts. We also have your template method, which consists of a series of equally spaced parallel lines drawn on a transparent film using any specified scale. So we'll be focusing on the interpolation or the analytic method. So let's have an example. So we have a map distance between two benchmark. AB is 15 centimeters and their elevations above sea level are given at 850.50 meters and 939.6 meters respectively. Assuming uniformity of slope between A and B, calculate the map distance from A where each of the following contours will cross the line between the two benchmarks. So this would pass through 860, 880, 900, and 920 meters. So let us refer to this figure. So we have 2 points, A and B. Their map distance is 15 centimeters. 15 centimeters is the distance between A and B on your map, not the distance or not the actual distance. Okay, so to solve for this, we now solve it by analytical method as assuming a constant or uniform slope. So with that, we now have a triangle here. So we have your difference in elevation. We have here the distance on the map. And then we have here your uniform slope. So to solve for our map distances, we solve first for the difference in elevation of points A and B. So that is now given as 89.1 meters. So by similar triangles, we can now solve for the map distance from point A to point 1, or this is now 860 elevation. So from there, so the two similar triangles, we now have DE of AB divided by the horizontal distance on the map is equal to DE, or difference in elevation of points A and point 1, or the 860 mark, and that is divided by x1, or this is in the figure h1. So substituting the values, we have now x1 equal to 1.599 centimeters, or approximately equal to 1.6 centimeters. So from our given, the contour interval now is at 20 meters, as it passes now, or the contour lines will pass through 860, 880, 900, and 920. So the interval is 20 meters. So from there, we can solve also by similar triangles. So points 1 and points 2, point 1 and point 2 will have a difference in elevation of 20. So it's 860 to 880. So we find now this distance between the 2 points. Okay, so from there, we now have DE, AB divided by H is now equal to the contour interval divided by the distance, or map distance per interval. So we get now x per interval as 3.37 centimeters. So for our map distances, we'll have now x1, or h1, is equal to 1.60 centimeters, which is the distance from point A to 860 meter elevation. So next we have h2 will now be equivalent to x1 plus your 20 interval map distance. So this will give us 4.97 centimeters, or this is our map distance from point A to 880 meter elevation. Then next we'll have x3 is equal to x2 plus the x per interval. So this will give us 8.34, or this is the map distance from point A to the 900 meter elevation. And lastly, we have x4, which is equal to 11.71 centimeters, or that is the distance between point A and the 920 meter elevation. So if you're going to check your modules, we will have the same or almost the same values. So this is another way of solving the problem in your module. Okay? So next example, determine the average slope between points A and B in the accompanying contour map. The contour interval is given at 20 meters. So the scale distance between A and B is 426.36, and the elevations of A and B are 390 and 300 meters respectively. So we have to express our answers for the slope in percent, degrees, gradient, mils, and grads. So for our contour interval, so we have here our index contour, which is 300. Interval is the distance between your two contours. So this one is 20. This is also 20. So the index is for every 5 contours. So 1, 2, 3, 4, 5. So that is 400. So 20, 40, 60, 80, 100. Okay. So to solve for our gradient or for our slope, okay, so to solve for our second problem, we first solve the difference in elevation of points A and B. So that is 390 minus 300. So the difference is 90 meters. So A is higher than B, so meaning the slope is moving downwards, or going down. So for the slope in percentage, this will simply be dE divided by h times 100. Or that is now the difference in elevation divided by the distance, or the horizontal distance between points A and B, which will give us an answer of 21.11%. So take note that this should be a negative value as we are moving downwards from point A to point B. So next, we have the slope in degrees. So we compute for the angle in degrees using arctangent of the vertical distance and their horizontal distance. And we'll have the answer at 11 degrees, 55 minutes, 10.3 seconds. So for next one, slope in gradient. This is simply equivalent to our dE over h, so that's 90 over 426.36. So what we will do here is to express this one in simple fraction. So you divide both numerator and denominator by the value of the numerator in order to have 1 is to 4.47, or the slope now can be written as a fraction 1 over 4.74, or by ratio 1 is to 4.74. And then for slope in mils, we could simply convert degrees into mils, or we could simply multiply the ratio of the vertical and horizontal by 1000. And we'll get a value of 211.09 mils. For slope in grads, we could also convert degrees to grads or gradients, or we could solve dE over h and multiply it by 63.7. And this will give us a value of 8. Okay, so that's it for Module 8 Topography or Topographic Survey. For your references, you can check all these websites. Thank you for listening. For your activities, please check the Google Classroom for the uploaded Evaluate activity.